So this is a warm-up to our addition reactions, and in particular our nucleophilic addition reactions. So what we've seen before is the reactivity of alkenes and alkynes, or ultimately the reactivity of nonpolar pi bonds. So we've got an example alkene here. So we're looking at a nonpolar pi bond. And we saw those, how they would react is that the electrons found in that pi bond would come out and react with an electrophile. So our alkene or alkyne would act as the nucleophile. And within the context of that, we ended up saying that there was no way that we could have the alkene come out and react with, say, a nucleophile. And that's because our nucleophile is a source of electrons, and our nonpolar pi bond is a source of electrons. We'd get a negative-negative repulsion, and so the reaction doesn't work. One of the issues that then pops up is, well, not all pi bonds are between two carbon atoms. So we would end up under a different circumstance where we're now looking at polar pi bonds. So what we want to think about is, how does that change the context of our reaction? Or does it change the context of our reaction? So the first approach would be to take those electrons and see what we could do with them. Okay, those electrons could very likely come out and react with, say, an electrophile, just like we did with the nonpolar pi bond. If we looked at how the structure would then interact with something else, what we're really then saying is that those electrons are really going to come up and hook up with our Y. Okay? Just like we would have said, say, in the other one, we're looking at our more negative carbon picking up the electrophile. Well, is that feasible? Is really the question that we then need to ask. Well, a lot of that's going to come down to the identity of our Y group. Well, what is Y? So a couple things need to pop up here. Number one, notice that it has lone pair electrons. Okay, so it could potentially act as a nucleophile or as a base. Okay, we also said that this is a polar pi bond. Well, the reason it would be polar is that whatever we know about Y must be more electronegative. And that would be our chi symbol for electronegativity. More electronegative than carbon. So what does that mean about its ability to then share electrons with, say, an electrophile? Well, that should already weaken it over the nonpolar pi bond. Okay, so, well, then that would suggest that our pi bond isn't going to come out and act with an electrophile. Instead, those electrons are probably going to sink back to our more electronegative element. Okay, and so really what we're suggesting is that we have a resonance structure. Whoops. We've lost the pi bond, and we put an extra lone pair on the Y, and then our carbon becomes partially positive. Okay. This is significantly different than the nonpolar pi bond, in that the nonpolar pi bond, it's a very weak resonance contributor. Here we have a much stronger resonance contributor because we know Y to be more electronegative. Okay? So this contribution then really causes this kind of shift, okay, in the reactivity that we would expect for the polar pi bond. Which means now that, whoops, we have our resonance structure, we want to see and think about how this could now react. Well, the Y could potentially act as a nucleophile, okay, but there's some things that kind of counteract that. Okay? Our counter to that would be that the electrons are already occupied in a pi bond. Okay? So that minimizes their activity with an electrophile. It's possible, but they're kind of minimized. So we would need a strong electrophile, much like we needed in the previous circumstance with our nonpolar pi bonds. More interesting, perhaps, is the carbon at the bottom. That carbon is now a really good electrophile, okay? Much more so than it was in the nonpolar pi bond. And that's because of that polarity. The Y atom taking the electrons away. So we have an electrophile in the polar pi bond situation that we did not have before. Okay, and so that's kind of neat. We're really zeroing in on the reactivity of this species as an electrophile. Okay, which then means if I'm going to go through and do a reaction, I need to react it with a nucleophile. But because I'm reacting it with a nucleophile, or as I'm reacting it with a nucleophile, the pi bond must break, so I'm also doing an addition reaction. And so what we can look at our polar pi bonds as reacting as is, yes, in an addition type fashion, but not in our standard electrophilic addition, in a nucleophilic addition. Okay? So we need to be reacting these with strong negative charges and seeing how that changes the structure. Neat little feature of it. Okay? So our primary driver in the next few sections is really what are decent nucleophiles. Okay? The primary functional group we're zeroing in on would be the carbonyl, which is really saying that our Y is actually an oxygen with 2 lone pairs. Okay? The electrons on the oxygen, or for that matter, an electronegative element like nitrogen up there, not particularly nucleophilic, but they could be basic. Okay, and we could talk about some of that characteristics. Again, our primary driver is right there with that carbon. We're looking at this as a strong electrophile. Okay. So, the rest of our chapters, actually before we get into the rest of our chapters, the one last thing we can do is we will also address what happens if we now bring that carbon near another functional group, say like a carbon-carbon double bond. Yes, no. Why does that look weird to me? Is what happens when we bring it near another pi bond. So if we draw this out, what are our interesting characteristics? This is sp2, this is sp2. We have conjugation of the system. That conjugation then means that this pi bond is now active. Okay? So something to be thinking about and being aware of, looking at resonance and how those functional groups can interact with each other. It's really getting split into 2 sections. We've got our strong nucleophiles, which are primarily talked about in Chapter 17, and then we'll look at our weak nucleophiles in Chapter 18 and seeing how they do these nucleophilic addition reactions. As our first step, a general mechanism might be useful. So we've got a couple different conditions we can run under. We'll focus first on just a standard carbonyl with a strong nucleophile. So because it's strong, we're likely running under, come on, this pen sucks, basic conditions. Okay, so with that strong negative, I want to find something positive to neutralize it as quickly as possible. We may not see anything obvious right away. This is why we can draw resonance. And we should see that that nucleophile can come in and attack and interact with that positive charge. Okay? So we need to be aware of our resonance, draw out our results. We have the nucleophilic addition. We've now lost the pi bond. Okay, so this is an addition with a nucleophile. We've lost our pi bond. We'll follow this up with a second step, and that's an important thing to note. This is a second step because if we added the acid in the first step, it would neutralize our nucleophile and we wouldn't have a strong nucleophile anymore. So we have to do this as a 2-step reaction. Not necessarily 2 mechanistic steps, 2 reaction steps. We need to see the 1, 2. That acid is used to go ahead and protonate our oxygen, and we would end up with our final structure. Okay. Could we do this same reaction if we were running under acidic conditions? Okay, well, we're still going to have the same carbonyl compound, except now with the strong acid present, I need to neutralize the positive first the lone pair from our oxygen is going to come out and react first. We would end up with our alcohol, and we'd still have a carbocation remaining behind. That carbocation needs to react with something negative. This is where our nucleophile can come in. It is typically a weak nucleophile, and the big signifier that we're looking at a weak is a couple things. No negative charge, and you'll almost always see hydrogen attached to the nucleophilic atom. Okay? The nucleophile can then go through and do its attack. Should have actually drawn those arrows on earlier. Okay, we'd end up with our product, or what is close to a product, but our nucleophile is still charged because of that hydrogen that was neutralizing it. The nucleophile does not want to be positively charged, steal electrons, and we'd end up with the exact same product that we had under the basic conditions. Except this time, note that we don't have any 1,2s. Okay, the acid and the nucleophile can get added in one step. As an example, we could do something like CH3OH with H+. Okay, and you would probably see the H+ written underneath the arrow and the CH3OH written above the arrow. If we did that same type of reaction under basic conditions, we'd do OCH3 negative as step 1 and as step 2 H+. You can get kind of yelled at mildly by some people because we have a charge structure there. You might see it better written as NaOCH3, putting in a counter ion to stabilize it. Okay. So our general mechanism, nucleophile attacks the electrophilic atom of our polar pi bond. That's it. The rest of the reactions follow that exact same pattern. Okay. The next part of this is to really get into and look at the electrophile. Okay, so are all of our polar pi bonds, or really our carbonyls, going to react the same? So we've got a smattering of carbonyls shown along this, and if we try to go through and identify our electrophilic site, I did try to be consistent in my drawing. We're trying to find our electrophilic atom. It is going to be the atom with the polar pi bond attached. Okay, a couple of tricky ones. Everybody almost always gets tripped up on the nitriles and the amines. Okay, and that's because you see those and you think, oh, well, I've got to react at the carbon down here. Well, no. You need to react where you have the largest differential in charge, and that's going to be looking at your pi bond. Okay, so keep your focus on the pi bond, at least for the moment. Okay, if we start switching with reagents, then you can start thinking about reacting in other locations, but the pi bond is going to be our primary driver. So then that, again, raises the question, should all of these react the same? Okay, after that, hopefully that was a little quiz question, we should have answered no. They should not all react the same. Now the trickier question, why should they not react the same? Okay, well, why is going to have a lot to do with what's different about them. Okay, and hopefully, I did this right, this portion is the same through pretty much all of them. Okay, we've got the same piece. We've got some hybridization issues popping up with our nitrile, but it's for the most part the same there. So what we're really saying is, how does that extra piece change the reactivity of that carbonyl? Okay, well, a lot of it's going to have to do with charge. Okay, so for instance, we have a charge over here. With that being a strong negative, what does it do? Donates into the carbonyl, which then makes the carbonyl unreactive. Okay, because it stabilizes it. We can't bring in a nucleophile to stabilize the carbonyl because there's already a quote-unquote nucleophile already attached to the structure. Okay, so we could look at charge. None of the other ones are charged, so we can't go there. So we could go to atom size. Well, we're looking at nitrogen or oxygen being connected for the rest of these, so there really isn't a size comparison that's going to work for us at least. We could try and do electronegativity. That's again going to be a little bit off because really what we're concerned about is the reactivity of the carbonyl carbon. Okay? And it's the same in all of these. What we're concerned about is how that purple part affects that carbon. So our size and electronegativity are kind of like mistreated or freakouts. So we could then move to resonance ability. Okay, well, what do we know about resonance? Okay, well, if there's electrons, they can donate inwards. So anything with electrons immediately nearby could donate electrons in. What would those electrons then potentially do? Well, they could then stabilize that carbonyl carbon, making them unreactive. Okay, or less reactive. If we compare them back to our charge structure, okay, they're more reactive than the charged one. Okay, you'll notice that I had 2 more blue arrows and yet I didn't highlight those, okay, or label those as unreactive. They weren't next to it. We'll come back to that in a second. The next part we could evaluate, okay, if we compare through, we're looking at R groups versus hydrogen. What color do I want? Let's go back to black. Back to black. What is the difference then between our R group and hydrogen? Well, hydrogen has no electrons. It cannot donate electrons into the structure. Okay, the R groups don't have electrons like the oxygen or the nitrogen, so they cannot donate in. So I would expect the R groups to be more unreactive, or sorry, more reactive than what's to the right of it. Okay, why? Okay, well, because there's no charge stabilization. If we push that further to our hydrogen, the hydrogen should be even more reactive than what's to the right of it because it has even less electrons than the R group. Okay, so we're kind of pushing this pattern where we have lowest reactivity and, at least at this stage, highest reactivity. So what's going on with those last 2? Okay, well, both of those have electrons to potentially donate in, but with chlorine as a halogen, should it donate electrons in? Well, no, that's an awful idea. It doesn't like doing that. If anything, chlorine is electronegative and withdraws electrons. But if it withdraws electrons, then that carbon becomes super positive, and I've generated a super reactive carbonyl carbon. Well, the oxygen we discussed earlier as sharing electrons inwards, wouldn't that stabilize the carbonyl carbon and make it less reactive? Well, if it does that, what do we see on the other end? We see another carbonyl carbon that's equally reactive. So instead of looking at it, focusing going to the right, let's see what happens if it goes to the left. Well, we would then generate an insanely stable structure that wants to leave. So we also have a very reactive species. Okay. So what we're trying to identify are the bits and pieces and how all those bits and pieces come together to change the reactivity of our carbonyl carbon. Okay, which then brings up the next question of why. Why do I care? Okay, well, the why I care is that if we take these reagents and drop them into a reaction with a nucleophile, we notice that some of them produce products right away, and some of them produce virtually no products. Okay? If we look at our rate, we're looking at insanely fast rates when my R groups are hydrogens. Okay? I'm also looking at generating the product at roughly 99%, okay, once I've achieved equilibrium. Okay? That's a pretty good situation. If we look conversely at making those carbons, how much product do I get? Virtually nothing. And my rate? Really, really small. Okay, or my rate constant? Really, really, really small. So if I change the environment of that carbonyl, I can change its reactivity significantly. Okay, and then again, well, why does that matter? Well, what are we reacting these with? Okay, I'm reacting them with a nucleophile. So if I go through and say, take my acyl chloride, carbonyl with the chlorine, and I want to react it, or say take one with the negative. If I want to go through and somehow do a reaction where my nucleophile is, say, H minus, which of these two is going to get me my product faster? H minus with the chloride or H minus with the acid salt? Well, the chloride will react faster. Okay. If it's going to react that much faster, I can probably use a milder nucleophile, okay, which means I'm more safe. So we're addressing each of kind of the features and how these things stack and how they can interact with each other. So we have to be thinking about these reactivities and how a subtle structural change can make a big difference in the end result. Okay, so our big summary out of chapter, I think it's 17, is looking at our hydrogen nucleophiles, our carbon nucleophiles, and then some other kind of weird things going on with it. So you're responsible for all of these reagents, and if you go through and look really carefully, what we're noting is that we're taking our carbon nucleophile, say that first case, and I'm directly nucleophilic adding it to the carbonyl carbon. If I go through and look at the next reagent, there's my nucleophile, it's adding, and for some reason I'm not seeing it. Oh, that's a good question. I wonder if I could ask a little quiz question about that. Okay. What about with the Grignard reagent? Well, I'm taking again a nucleophile and I'm having an attack. Okay, there's my hookup. So we're doing the exact same pattern again and again and again and again. Okay, and it's just recognizing those patterns and how things are coming together. We will point out with that last one that we do get a little bit of an odd situation. We do have our standard kind of addition where the nucleophile attacks our electrophilic carbon, but what happens if I put it near another alkene? Notice that I have a second electrophilic site, and depending on my conditions, my nucleophile can attack either the second site or the first site. Okay, so we have to be aware of those conditions. That's really known as direct 1,2 or conjugate 1,4 addition. So we're putting a carbonyl next to an alkene. Okay, we'll think back again to the reactivity of our carbonyl. Our carbonyl was reactive because it's withdrawing electron density. Okay, well, if it withdraws electron density from that carbon, what is it doing to subsequent groups? Well, it's also withdrawing electron density. That means we end up with two sites of electrophilic character, the carbonyl carbon and what is known as the beta carbon. Because if we count out Greek letters, it's at the second position away from our carbonyl. Two sites of reactivity means two possible products. Okay, the same kind of concept happens when we think about placing an alcohol next to a carbonyl. Put an alcohol next to a carbonyl, we get a carboxylic acid. The acidity drastically changes. Okay, so that's where we're getting this kind of differentiation. If we use stupidly strong nucleophiles, we get the direct addition, our 1,2. If we use quote-unquote strong nucleophiles, that's when we start to see the 1,4 kind of come in and interact. So we have to be a little bit more careful about our analyses when we go through and do this. So one of those is kinetic and one of those is thermodynamic. So if we break down our mechanism, we can look at how it pieces out. We can look at all of those intermediates. So in deciding which one of those is favored, we could evaluate the stability of our products and decide which ones are thermodynamic. Okay, well, between those, hopefully you would say the most reactive thing still there is the pi bond, our nonpolar pi bond. Okay, and in the red case, or what will soon be the red case only, our pi bond is more substituted. More substituted means more stable. If we have a more stable product, that is our thermodynamic. And if we think back to the addition reactions that we did with the butene, okay, and we could look at the intermediate formed and say, well, the intermediate formed allowed us to differentiate between kinetic and thermodynamic. So let's go back and look at the intermediates formed between these. So here's our intermediates. We want to compare them and say, okay, well, which one is more stable than the other? And if it holds to our butene or butadiene comparison, we would assume that the blue one is more stable. Okay, and we should immediately see we've got a problem because the red one's more stable because it has more resonance. Well, crap, how do we get the blue one to be a kinetic product? How is it reacting faster? So we've lost the ability to look at our intermediate. Okay, so really what we should be focusing on is what we remember from seeing with our Diels-Alder reaction. When we looked at the Diels-Alder reaction, we had two possible products. We had an endo and an exo product. And since it all happened in one concerted step, okay, we ended up with kinetic and thermodynamic, and that was all dependent on the transition state, on what was happening as we moved through. Since in our reaction, since in our reaction we've already established what's happening through it, we can go through and say that our clutch step is happening at that very first stage. Something about the transition state for our red mechanistic arrows, okay, would suggest we're looking at our, I totally color-coded this backwards, looks at our kinetic product, and the other one ends up being our thermodynamic. Okay, so we have to decide why. Why is the transition state for our red one lower in energy than for our blue one? Okay, well, what's happening in the red one? The red one's taking a nucleophile, okay, which we can make a little more obvious by saying it's negative, and having it attack our carbonyl carbon. And the blue one, we're having it attack an alkene carbon. What is the difference between those? Well, the partial positive charge on our carbonyl carbon is going to be bigger than the partial positive charge on our alkene carbon because it's a polar pi bond and that electronegative oxygen is pulling electron density away. Okay? So that's our transition state. Okay? If we wanted to go through and try and quantify this to help us figure out what's going on with this, we have to think back to looking at our pKa's and deciding which side of the reaction was favored. Okay? It gets a little bit tricky in this circumstance, but it'll work. Okay? So if we looked at our acid strength, we could compare our reagents first, decide which one's the acid. The lower the acid, or the lower the pKa, the more acidic. So HCl is our acid, so we can ignore the water. And we go through and do the same thing on the other side. The lower the pKa, H3O+, that is our conjugate acid. And then we compare those two numbers and say which one of those two is lower. Sorry, not lower. Larger, another L word. The bigger it is, the less acidic, and the more stable. Where do our reactions favor? The more stable products. So if we looked at this reaction, we could say it favors our products significantly because on our logarithmic scale, we're looking at a difference of, what is that, 5.7 powers of 10. So that's a pretty significant order of series of orders of magnitudes favoring our products. Okay? If we go back to our overall reaction and say, okay, can we use that to our understanding to help us through this? Okay, we need to be looking at, again, our conjugate acids, because it's a little bit easier to work with. We could say the pKa of our conjugate acid, something like about 16. Okay, well, we aren't looking at an acid to start, we're looking at a nucleophile. Okay, so we should take that to its conjugate acid and evaluate its pKa. Well, in this circumstance, do we know what that pKa is? No, because we don't know what the nucleophile is. So we have to introduce, to understand direct versus conjugate, what is happening with our nucleophile. Are we looking at a strong nucleophile or a weak nucleophile? And our pKa can give us some information about that. Okay. So we smack that all together and try and go do our interpretation. Our conjugate acid of our product ends up putting us at a pKa of about 16. If our nucleophile was H-, the conjugate acid of that nucleophile is massive, stupidly big. Okay? So if we're looking at how the reaction favors, remember, because we're acting our bases, inverses on us, we want to go towards the side of the reaction that gives us our smaller pKa, which I know is a little bit weird, okay, but that's the way we want to process this one. Okay, so what does that mean? Well, I'm looking at starting at 50 versus 16. We're looking at multitudes of orders of magnitude difference here, which means if we look at that very first step of the reaction, okay, now all of that is pretty much nonsense. This very first step, that reaction heavily favors the products. Okay? So much so that what we will end up seeing is only the formation of our kinetic product because of the lower transition state. Okay? Well, what happens if we change the nucleophile? Okay? If we shifted it to a carbon nucleophile, well, carbon nucleophiles are equally massive. So again, this favors the extreme formation of our products. Whichever one of our products has the lower activation energy or our lower transition state is going to determine the product we get. So our nucleophile is really driving this. Okay? As we continue to shift our nucleophile around, we eventually reach a point where something different happens here. So we have another carbon nucleophile, but this is now, whoops, let's ignore that for a second. We have another carbon nucleophile here, but this time our pKa is something like 9.4. And we now see a difference in a comparison here. Okay? This equilibrium favors actually the reactants, not the products. So what does that mean? Okay, well, our reaction will still go through to form our kinetic product first, but now it can reverse. This goes back to forming our reactants. When that reaction reverses, I get another opportunity to go through and make the thermodynamic product. Because the thermodynamic product is lower in energy than our kinetic product, it is effectively always irreversible. That means once I've made it, I cannot undo it. The kinetic product can be reversible depending on the reagent. If it is reversible, then the thermodynamic product is the one that wins out, and I end up getting the 1,4 addition versus the 1,2. Okay, that is a very nuanced review of that, and we'll see it again in class when you ask questions about this. Ultimately, you're responsible for knowing which ones add reversibly and which nucleophiles add irreversibly. Okay, because this is going to determine whether we get the 1,4 or the 1,2 additions. So we've got a nice little table coming from your textbook that shows the irreversible nucleophiles and the reversible nucleophiles. Okay, again, the reversible nucleophiles, okay, will result in the thermodynamic product because that product is irreversible. Yeah, I know, that's a fun phrase, but let's say that again. Okay, these nucleophiles are reversible, which means I form the thermodynamic product, which is irreversible. This reversibility that is getting referenced at the very top here is referencing the formation of our kinetic product. Okay? If it reacts with the kinetic reversibly, okay, with those strong nucleophiles, then I get the thermodynamic product. If it adds irreversibly, then what I end up with is the kinetic product instead of the thermodynamic, because I can't reverse over here. Okay. Bottom line, every single reaction makes the kinetic product first. You then must decide, can the kinetic product reverse directions? If it can, we get the thermodynamic product. I know, it's lovely logic, but that's the way it works out. Okay? Last thing we'll bring in here, oxygen, nitrogen, and what is known as your Gilman nucleophiles, okay, and how they react with our carbonyls. These match under that reversible system here, and so what we end up expecting out of them is the thermodynamic product. Okay, in all cases with these nucleophiles. One of the big issues that pops up here is that we get a lot of equilibrium. Okay? And that fun little word association here, you should think back to your Gen Chem class, and you probably hated equilibrium. Okay? When we're looking at these reactions, it's not a why would it happen or is it happen, but it does happen. Okay? And that is a bit unfortunate, but you're really just going to have to learn to deal with it. Okay? In that dealing with it, do not break your Lewis structure curved arrow rules. Those are insanely important. You cannot lose track of those. Do not exceed octets. Do not lose octets. Okay? Move electrons from a source to some place that lacks them. Okay? So we've got those rules summarized down there for a big reason. After that, we've got our oxygen nucleophile reagent summaries and our nitrogen reagent summaries. These become important if you're moving into biochemistry. The oxygen chemistry, we're really driving in at acetals. Acetals are the organic chemist's way of referencing carbohydrates. The nitrogen chemistry often pops up in biochem when you're looking at enzyme catalysis. Okay, so it's an important chemistry to be aware of, and it will show up there. This last slide is another big spider diagram that just shows everything that you could possibly go through and see. It is helpful, a bit daunting and overwhelming, but this shows pretty much all the types of reactions coming from your keto base functional group. And with that, we are done.